Okay, today we're going to talk about two very important things in chemistry. Number one, valence bond theory, and number two, hybridization, both of which are going to be part of module 1.2.3.1. So let's start with valence bond theory. So you might ask yourself, what is valence bond theory? Well, valence bond theory is a kind of mathematical description that we can use to describe bonding. And we're going to do this in terms of orbital overlap, meaning we want the orbitals from these atoms to come together and try to make a bond. The more they come together, or the more they overlap, the stronger that bond is going to be. One of the reasons why people like valence bond theory is it's mathematically simple, relatively speaking, and it also gives rise to things like bond lengths and bond strengths, which are experimentally measurable quantities. And the idea is that the positions of the nuclei are pretty fixed, right, here and here, because the protons and neutrons aren't really moving. It's the electrons on the outside that are doing their thing. But the position of maximum kind of overlap between the orbitals is going to dictate how far away those two nuclei can be. Okay, and so what I'm going to do now is show you a figure to illustrate how valence bond theory works. So let's pretend that I have two hydrogen atoms. Okay, here's one, and here's another. And they're going to combine to give me H2, the molecule. Okay, it's a very simple reaction. We're going to go from right to left on this graph. Okay, and so my x-axis here is the internuclear distance, which I can call R. And the y-axis is my energy, or potential energy. So let's assume that these two atoms, these two hydrogen atoms, are really far away. Okay, so far away that there's like no attraction or repulsion between them. They're all just doing their own thing. Okay, so we would say that the potential energy between them is exactly zero. Okay, but as I draw these things closer and closer and closer and closer and closer together, they start to be attracted to each other. Why? Because the proton of one, the nucleus of one, is attracted to the electron cloud, the electrons on the other, and it kind of draws them closer together. Okay, and so as I go this way, as the distance between them decreases, they get more and more attracted to each other, and the energy between them decreases. Okay, so all of this represents attractions. Eventually, they get pretty close together, and this area here in the middle represents the overlap between those two orbitals. Okay, and so right now, they're both pretty happy because they can share the electrons and all of the good interactions are maximized. If I bring them even closer together, then I have a problem. Okay? Now I start to get repulsions between the electrons, and that's going to cause the energy to shoot back up. And so that's where this repulsion comes in, and that's going to be unfavorable, so the energy goes upwards again. So this point right here represents the best possible situation. Okay, this is considered the minimum energy, or lowest energy. And so the distance between where I started up here and where I ended down there is called the bond energy. The place on the y-axis where that happens is the bond energy. On the x-axis, the distance from the origin to where that minimum is called the bond length. Okay, and so every bond has two characteristics, a bond length and a bond energy. So let me give you an example of how valence bond theory might be used in practice. Let's say we were trying to describe the bonding in H2S, hydrogen sulfide. Okay, well, if I use Vesper theory, stuff we talked about earlier, okay, I would draw the Lewis structure, and I would have two bonded pairs and two non-bonded pairs. So this would be an AX2 E2 system, which means that the shape would be bent or angular. The angles would be about 105 degrees or so, but certainly less than 109.5. Okay, now let's do it doing valence bond theory and see how it compares. Okay, so as far as valence bond theory works, I have to worry about the valence electrons for hydrogen, which are 1s1, and the valence electrons for sulfur. So sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. The point is that the valence electrons are in the third energy level, 3s and 3p. And if I look at the 3p subshell, I have 4 electrons in it, okay? These are the ones that are going to be involved in bonding. So what I tried to do is show you those orbitals here. Okay, here's one p orbital, here's another p orbital, here's the third p orbital. These are all perpendicular to each other. Those have to overlap with the 1s hydrogen orbitals. And so the point is that I can make a bond here, and I can make a bond here, and the angle between the hydrogen, the sulfur, and the hydrogen would be expected to be about 90 degrees. So I get very different results. Valence bond theory predicts that the angle should be 90 degrees. VSEPR theory predicts that the angle should be closer to 105 degrees. Okay, so who's right? Well, I don't know. We have to look at the experiment and see what that says. Okay, if you actually do an experiment to measure the bond angle, it's pretty close to 92.1 degrees. Okay, and so in this case, valence bond theory is a little bit closer than VSEPR theory. All right, so moving on, we're going to talk about a different topic now. Hybridization only exists on paper. It's kind of a mathematical construct that we use to try to explain things mathematically, but it doesn't really easily lend itself to like a natural interpretation of things. Okay, and so the idea is that all of these orbitals for all of these atoms and the electrons in the atoms are really just mathematical functions. And so I can take these orbitals and just combine them mathematically, if nothing else. And I can make hybrid orbitals using atomic orbitals any way I want, as long as I satisfy two conditions. Okay, the first is that the total number of orbitals has to stay the same. And the second is that the total energy of the system stays constant. Okay, as far as we're concerned, we can use hybridization for both bonding pairs and also for non-bonding electron pairs. So here's the idea. Atomic orbitals only work for atoms. There's some pretty bad agreement between the theory and the experiment, at least in terms of bond energies and bond angles and bond lengths. Okay, so let's invoke different kinds of hybrid orbitals. Okay, for example, we can have SP hybridization. In SP hybridization, we're going to start with an s orbital and a p orbital and combine them. Okay, and we can combine them in such a way that they add constructively or they can add destructively. Okay, and so in this figure, you can see how this works. Here's an s orbital in red. Here's a p orbital in blue. And you can have two different orbitals. This one represents destructive interference. You can see how when I bring them closer together, the part that they should have overlapped actually got smaller, so that's destructive. Here, as I bring them closer together, the part that they share got bigger, so that's constructive. Every hybrid orbital has a certain character. The character really represents what percentage of the hybrid orbital is found in an existing atomic orbital. Okay, and so for example, in our SP hybridization case, it was one s orbital and one p orbital. That's like 50% s and 50% p, right? There's one of each. Okay, and we're going to use the character to describe the different kinds of orbitals that are possible. Okay, and so one possibility is SP hybridization, which has 50% s character, 50% p character. But what I'll show you now are some other hybridization schemes. Here's how hybridization might be used to describe bonding. Okay, here's BeH2, beryllium hydride. On the top left is the unhybridized beryllium and two hydrogens. Okay, and so just to refresh your memory, hydrogen is 1s1, beryllium 1s2, 2s2. So the point is that the beryllium would only have electrons in the 2s subshell and nothing in the 2p. I'm going to take this 2s and this 2p and combine them to make sp hybrid orbitals. Okay, two sp hybrid orbitals. And since I had two electrons to begin with, okay, one here and one here, I'm going to put them in these hybrid orbitals, one here and one here. And now, when those hybrid orbitals combine with the hydrogen 1s orbitals, okay, they can make a bond here and here and have much better orbital overlap and a much stronger bond. So here's an example of something with a different kind of character, a different kind of hybridization. This is SP2 hybridization, where we're going to combine one s orbital with two different p orbitals, right? That's what the p represents. So now it's going to be 1/3 s and 2/3 p. And you can see this schematically on the bottom. Okay, here's an s orbital. Here are 3 p orbitals, but I'm just going to use these two to combine with the s. So now I have 3 orbitals that are hybrid, right? Partially s and partially p, but mostly p, right? 2/3 p, 1/3 s. The purple p orbital stayed unused, right? So that's there, it's unchanged. Now I have 3 things in space. These are going to have a different geometry. Instead of being linear, like the SP hybridization was, this is going to be more like a trigonoplanar geometry, where the angle is going to be about 120 degrees. Okay. Another possibility is something called SP3 hybridization. And so what happens in SP3 hybridization is you have one s orbital, just like we had before, and 3 different p orbitals, but we're going to use all the 3 p orbitals. So since I have 4 atomic orbitals to begin with, I have to have 4 hybrid orbitals to end up with. And so each of these is going to be 1/4 s and 3/4 p, right? So as far as character goes, that's how they are. And since I have to arrange these 4 things to be equidistant in space, this is going to have to adopt a tetrahedral geometry. It is possible to have hybridization with other orbitals besides s and p, like the d subshells, but these usually have to do with expanded octets. Okay, and so you might have, for example, something like d SP3 or d2 SP3, where I might have to use 10 electrons to make 5 bonds in the case of DSP3. Or maybe I have 12 electrons that I need to make 6 bonds in the case of D2SP3. And so even though we use these things, the experimental evidence is actually pretty weak as far as like justifying that they're there. Here's a summary of all the different hybridization schemes, so you can see exactly how they fit in. Okay, you can have SP hybridization, SP2 hybridization, or SP3 hybridization, as well as DSP3 or D2SP3. Typically, things that are SP hybrid have a linear geometry. Things that are SP2 have a trigonoplanar geometry. Things that are SP3 are in the tetrahedral family. So it could be tetrahedral or trigonal pyramidal or bent, depending on how many bonded pairs and how many non-bonded pairs there are. Things with 5 bonds or DSP3 hybridization tend to be trigonal bipyramidal. And finally, things with 6 bonded pairs tend to be octahedral. Okay, so after you've seen all this, you might ask yourself, why hybridization, right? Why are we doing all this and why do we care? Okay, well, a couple of reasons. You get much better overlap than if you use just regular atomic orbitals in terms of making the bonds stronger and having these atoms come together in the first place to make these bonds. And we also have better agreement with experimental data. Okay, we can compare the results from experiment and get much better comparison between that and what we would predict using hybridization if we didn't have hybridization and just use regular atomic orbitals.